Hello everyone, welcome back to this another video. I hope that everybody is safe and doing well, and we are still taking the necessary precautions to stay safe wherever in the world that we are. Today we want to look at how we can use differential equation to model linear motion, and we're going to explain just how an object in motion can be modeled using linear differential equation, and we're going to use the concept of separation of variables to solve a linear motion problem. So here I have an object and my object here is on a surface. Now I know that my object is going to be, there's going to be a weight that is acting down from the center of gravity of my object due to gravity. I'm going to call that mg. And based on what you would have done before, we know that there's going to be a opposing force pushing back. That's the normal force. Now, let us say that my object is moving in this direction. So there is some force, Fw, that is pushing my object in that direction. Right? There's going to be some resistance force, Fr, that is pushing back on my object in the opposing direction. Now, the mere fact that my object is not falling through my surface, we know that the sum of forces in the y direction will be equal to 0. Now, my object is moving in this direction. So I know that the sum of forces in my x direction according to Newton's law of motion is going to be equal to mass times acceleration. Now, my forces acting in the x direction is going to be my force that is causing my object to move, and my frictional force that is going in the opposite direction, which is going to be equal to mass times acceleration. Now, let us say that my resultant force here is actually some function of x. So let us say my sum of forces in my x direction is some function of x, f of x. Then f of x is going to be equal to mass times acceleration. Acceleration can be expressed as some, in terms of x, as, let me write back my f of x, v dv dx. So my acceleration can be expressed as v, the derivative of velocity with respect to my function of x, such that f of x is equal to, let me just quickly erase. I know that my mass is going to be a constant value. My mass is going to be a constant value. So I can say 1 over m times my function of x, which is my resultant force, is equal to V dV dV dx. And so when expressed in this form, I am using, this becomes a differential equation. And I am using my differential equation here to model some object that, of course, is in motion. Now, how can we use differential equation really to not only model but solve question as it relates to objects that are in motion? Let us look at a question. Let us look at a question. Let us look at a question. Okay, so let's look at this question. The velocity of a skydiver, V of t, who is parachuting so the velocity of a skydiver who is parachuting down to earth is satisfied by the differential equation dv dt plus 2v equals 36. Where v is velocity, and t is time in seconds, given that the initial velocity is equal to 45 meters per second, express v in terms of t when t is measured in seconds. So we're being asked to express v. Let's just make some simple correction here. Very good. So the velocity of a skydiver, v of t, who is parachuting down to earth is satisfied by the differential equation. dv dt, and we know dv dt here is acceleration. We can express acceleration of the rate of change of velocity with respect to time, plus 2v is equal to 36, where v is velocity and t is time. Given that velocity, the initial velocity when time equals 0 is 45 meters per second, express v in terms of t. So we know that the skydiver is diving down, and he's satisfied by the differential equation dv dt, which we know this is acceleration with the rate of change of velocity with respect to time, plus 2v equal 36. So here we have dv dt plus some function of t, let's say some function of t times v equals some other function of t. And so we know that this is really satisfying a differential equation where they are asking us to express v in terms of t. Looking at this differential equation, we realize that it is not possible for us to solve this, express v in terms of t by using separation of variables. And so what we have to do is find our integrating factor, right? And I'm going to call my integrating factor mu, where mu is equal to the e to the integral of gt with respect to t, right? So I know that mu, my integrating factor mu, is going to be equal to e to the integral of my gt is whatever is in front of my v, so that's going to be the integral of 2 with respect to t, which means that my integrating factor mu is going to be e to the 2t. Now I am solving for v with respect to t. So let's go back to the differential equation, and we're going to solve for v with respect to t. Now that I have my integrating factor, I know that v times my integrating factor e to the 2t is going to be equal to the integral of is going to be equal to the integral of 36, which is my qt here, my function q of t, 36, times my integrating factor e to the 2t dt. So I'm going to solve this for my function v with, of course, respect to t. So v times e to the 2t is going to, this is a constant, so I can pull it out of my integral sign, 36 times the integral of e to the 2t with respect to t. So v e to the 2t is going to be equal to 36. I know that I am integrating e to the 2t. I'm going to take the top, differentiate it, and divide by the result. So it's going to give me e to the 2t over 2 plus my constant of integration, c. I know 2 into itself goes 1. 2 into 36 goes 18. So I'm going to be left with v times e to the 2t is equal to 18 times e to the 2t plus my constant of integration c. I want to find v, so I'm going to divide by e to the 2t, and I'm going to do the same thing here, e to the 2t. Now where do I go from there? Where do I go from there? So we know that we're dividing through by v times e to the 2t is equal to 18 times e to the 2t plus c, and we want to find v with respect to t, so we're dividing through by e to the 2t, we're dividing through by e to the 2t. So this is going to cancel, leaving v, and v is going to be equal to e to the 2t will cancel there, leaving 18 plus c over e to the 2t. Well, let me just fix my c here. V is going to be equal to 18 plus c. I'm going to bring my e to the 2t up, so it's going to be e to the negative 2t. And here I would have just expressed v in terms of my function t. Now let us look at another question. Just look at another question. And this one is going to be a little bit different, but still a good question for us to look at. So it says, a toy truck of mass 0.2 kilogram is traveling on a straight line. In a straight line on a horizontal floor. The truck is modeled as a particle, and the resultant force of the truck is modeled as 1 over 10 times x, 1 over 10x times 6 minus 3x squared. If the truck comes to a sudden rest at x equals 6 meters, they want us to find an expression for u square, where u square is being expressed as velocity squared, and the acceleration of the truck at x equals 4 meters. Right? So I'm going to just do a quick sketch. This is my toy truck on a flat surface. I know the toy truck is expressing, and I'm going to be using gravity as 10, let's say not 10, as 9.8 meters per second squared. There's going to be some weight that is being exerted down on this object due to gravity. Let's call that mg. The mere fact that it is not falling through, we know Newton law of motion that says for every action there's an equal but opposite reaction. There's an equal and opposing force. That's my normal force. So let us say that my object is going in this direction. There is some force due to work that is pushing on the object in that direction, and of course there's going to be some resistance force that is pushing back. Now, according to Newton's second law of motion, The sum of forces in the x direction is going to be equal to mass times acceleration. Now the forces, the resultant forces is being modeled as 1 over 10 x times 6 minus 3x squared. And that is equal to the mass, which in this case is 0.2, times acceleration, which I can express as v dv dx. Now, I am being asked to, the question says we're expressing velocity squared as u. So we're going to quickly change v here. And in according with the question, we're going to use u du dx. I can divide both sides by 0.2. Let's do that. 0.2. And that is going to leave me with u du dx is equal to 0.5 x times 6 minus 3x squared. So now that we have divided by 0.2 and we know that we're going to get 0.5 x times 6 minus 3x squared is equal to u du dx. Let's take it from there. We can simplify what we have on this side by expanding our bracket using our law of distribution. So when I expand, I'm going to get 3x minus 0.5x times 3x squared is going to give me 1.5 x cubed, which is equal to u du dx. I can solve for u. I can solve for u squared by using separation of variables, because looking at this, I notice that it is separable. So I can actually solve for u squared by doing that. So let's separate. So u du is equal to, I'm going to bring my dx here, 3x minus 1.5 x cubed. Now I can integrate both sides. So if I integrate what I have here, it is going to be 3 over 2 x squared minus 1.5 over 4 x to the fourth. And we're applying our basic rule of integration with our powers here, plus my constant of integration c is equal to u squared over 2. Right, I want to find u squared, so I'm going to multiply through both sides by 2. So 2 will cancel here, and u squared is going to be equal to, 2 is going to cancel here, leaving 3x squared minus 1.5 over 2 x to the fourth plus c. So here I have just find an expression for u squared, which is 3x squared minus 1.5 over 2x to the fourth plus c. And you know, we could fix that up by putting the higher power first. So let's do that. So u squared is equal to, and I'm just going to simplify the fraction that I have a little. 1.5 divided by 2 is going to give me quarter. It's going to give me a quarter x to the fourth. Alright, and that should of course be negative. Plus 3x squared plus 3x squared plus c. And not a quarter here, but 3/4. 1.5 is 3/4 of 2. So this is my expression for u square, where u square is actually representing velocity square. The question is then asking us to find the acceleration at the chuck of the chuck at x equals 4 meters. But we know that the chuck came to rest at x equals 6 meters. Alright, so the chuck came to rest at x equals 6 meters. So the velocity of the chuck was 0 when x was 6 meters. Right? So we can use that to find what our constant c is by saying 0, and of course velocity is being represented by u in this case. 0 squared is going to always be 0, is equal to negative 3/4 times 6 to the fourth plus 3 times 6 squared plus c. So that's going to give me negative 972 plus 108 plus c, and all of that of course is equal to 0, which means that c is equal to 864. So u squared is actually equal to negative 3/4 x to the 4 plus 3x squared plus 864. Now that we have this, we can move into the next question to find the acceleration of the chuck at x equals 4 meters. So u squared when x is equal to 4 meters is going to be negative 3/4 times 4 to the 4th power plus 3 times 4 to the 2nd power plus 864. Right? And of course we can simplify all of what is happening here. This is going to give me negative 192. 4 squared is 16. 16 times 3 Let's go to our calculator very quickly. That's going to give me 48, and I am adding 864. Which is going to give me u squared being equal to 720. So I can square root both sides, which means u is going to be equal to 26.83 meters per second. Now, I want to find acceleration. The mere fact that the object came to rest, it means that the initial velocity that we have working with here is going to be 26.38 meters per second, and we can write that 26.83 meters per second, the initial velocity, and we're calling that ui, u sub I, and our final velocity would have actually been 0 because the object came to rest after traveling 6 meters. This was the velocity of the object at 4 meters, so of course it has to be the initial and this is the final. I know that v final velocity is equal to, and we're using u, I keep going back to v because that is what I'm used to, is equal to initial velocity plus acceleration times time, which means that acceleration is equal to final velocity, which is 26.38, minus initial velocity over let's go back just a little bit. So we have our initial velocity and we have our final velocity. We can't use this formula as we don't have anything with respect to time, but I know that final velocity squared is equal to initial velocity squared plus 2 times acceleration times displacement. Right? My final velocity here so I can transpose this to, of course, find what my acceleration would be. So since my final velocity is 0, so it's going to be 0 meters per second minus my initial velocity, which is 26.38 meters per second, all divided by 2 times the distance is actually in the question is 4 meters, so I'm dividing by 4 meters, which is going to give me negative 26 point, I keep saying 38, this should be 0.83, 0.83 divided by 8, which is going to be 3 meters per second squared. 3, let's approximate it to the nearest whole number as 3 meters per second squared. And that is the question for you. When we're going to continue looking at problems, and so we'll get enough practice.